is the IMS public lecture on cold-atoms and quantized processes. It's my great pleasure to introduce the speaker for today. Speaker is Professor Jakob Ingvarsson. I hope I'm getting the right pronunciation. So, Professor Ingvarsson obtained his PhD from the University of Göttingen, and he was a professor of theoretical physics at the University of Iceland at Reykjavik before taking his present position in Vienna in 1996. So he's now the professor of mathematical physics at the University of Vienna and also the scientific director of the Erwin Schrödinger Institute for Mathematical Physics in Vienna. I believe that Professor Ingvarsson is our first Icelandic speaker for this series. So we're very happy that we have a speaker from Iceland, well, working in Vienna. Now, Professor Ingvarsson has held many visiting positions. He was in institutions in Germany, France, Italy, and the US. And he was also the vice president of the International Association for Mathematical Physics between 2000 and 2005. And he has served on many boards and committees, including the board of the Austrian Science Fund and the steering committee of the Niels Bohr International Academy in Copenhagen. He's the editor-in-chief of Reviews in Mathematical Physics and also an editorial board of the Advances in Theoretical and Mathematical Physics. He has received many prizes, among them the Levi-Conan Prize of the American Math Society and the Erwin Schrödinger Prize of the Austrian Academy of Sciences. And he's also the corresponding member of the Academy of Sciences in Göttingen and the Royal Danish Academy of Science and Letters in Copenhagen. So I'm sorry, so obviously there's a lot of this. So, I mean, there are a lot of honors. So we're a very distinguished speaker for today. So I think I'll leave it to now to Professor Ingvarsson. Tell us about cold-atoms and quantized processes.
Thank you very much, Professor Tan, for this kind of invitation. It's really great to be here. It's a great honor for me to speak here in the Lion City. This is, well, I should first say, because I see you're very expert, that this is announced as a public lecture and not as a physics colloquium. So I hope you bear with me that there will be very few formulae and no integrals. Anyway, I'm also aware that there is quite some activity in quantum physics here. In fact, today I visited the Center for Quantum Technology. It was very impressive seeing all these people there. And there was even there was even a program 2.5 years ago about rotating Bose-Einstein condensation and a public lecture on the cooling of atoms given by Professor Christopher Food from Oxford. But I think maybe that my approach to it will be more from the theoretical side and have certain different accents, so I hope there will not be too much overlap. Anyway, so the hero of this whole topic is really Albert Einstein, who is, as you know, most famous for his work on relativity theory and the theory of the very fast and the very heavy. But he was also a pioneer in the theory of the very small, namely quantum theory. And I would just like to recall that there are these very significant contributions. The photoelectric effect, 1925, for which he received the Nobel Prize. Specific heat at low temperatures, 1906. Then this pioneering paper here in quantum electrodynamics in 1917. and not last but not least in this list here, the paper on Bose-Einstein condensation in 1924. Now, Einstein is very often, well, in fact, criticized for being a critic of quantum theory, and it's true that his attitude was not always very favorable, but his extremely critical and penetrating analysis has in fact been extremely important for subsequent developments and the modern theory of quantum information. For instance, it really owes a lot to the discussions with Niels Bohr and the Einstein-Podolsky-Rosen argument. Okay, but let's continue with Bose-Einstein condensation, and the history starts in 1924 when the Indian physicist Satyendranath Bose derived Max Planck's radiation formula for the radiation from a black body from a new idea about the statistics of light quanta. Now this paper, that's something that many of you know here, it was written in English, and it was Bose sent it to Einstein, and in order to make it widely known in the scientific community, Einstein translated it into German. Nowadays we have to do it the other way around, unfortunately. Anyway, what was maybe more important was that this idea triggered Einstein to apply it to material particles, not just to photons, to particles of positive rest mass, and in this way he discovered Bose-Einstein condensation. So it is just renamed after both of them, although it was really Einstein who discovered the condensation, because there is no such thing with photons. Now, what is Bose-Einstein condensation? Here is a very brief summary of that. Namely that, first of all, one should be aware that under normal conditions, when normal, I mean normal temperature, pressures like we are experiencing here, the atoms of a gas are distributed among very many quantum states, and every single state is therefore occupied by relatively few atoms. In Bose-Einstein condensation, on the other hand, that's the hallmark of Bose-Einstein condensation, that a single quantum state becomes macroscopically occupied. An important prerequisite is that the atoms are bosons. Most of you will know that the atoms, or rather elementary particles, or particles, they come in two kinds, bosons and fermions. They are distinguished by their internal angular momentum, the spin. If it is an integer multiple of Planck's constant, then there are bosons, but particles like the electron, which have half integer spin, are fermions. And it's important that we have bosons, although nowadays one also does very fancy experiments with bound states of fermions, but that is a more advanced topic I'm not going to talk about. Now, for Bose-Einstein condensation, extremely low temperatures are required, of the order of 1/100th of a million of degrees of Kelvin, of 1/1,000,000th of a degree of Kelvin, 10 to the -8, and creating such conditions was in fact a very difficult experimental task, and it was first accomplished in 1995. 70 years after Einstein's theoretical prediction. The next maybe to discuss here briefly is, why is Bose-Einstein condensation so interesting? Well, I would say one way of putting it, at least the first, is to say that in Bose-Einstein condensation, macroscopic quantum phenomena become visible on a macroscopic scale. Among these phenomena is superfluidity, which is a particularly spectacular phenomenon, and one of its manifestations is quantization of vorticity, which I'm going to talk about a little more later, when Bose-Einstein condensate is set into rotational motion. Last but not least, and this is what makes it really so difficult to analyze theoretically, is that Bose-Einstein condensation is a very subtle example of a phase transition which is accompanied by a breakthrough of a continuous symmetry. The symmetry is here of a rather abstract kind. It's a gauge symmetry, but this is one of the mathematical difficulties here. I will say a little bit more about that later. Let's make here a little historical remark, well, in fact, an important historical remark, namely that superfluidity was first discovered much earlier. That was already in 1938 by Piotr Kapitsa. And shortly afterward, Fritz London suggested that superfluidity was related to Bose-Einstein condensation. However, it is, of course, clear that liquid helium is very far from the ideal model that was considered by Einstein. And it was, in fact, very controversial whether this had anything to do with Bose-Einstein condensation in the sense of Einstein. And as a big research topic, Bose-Einstein only took off when it was became possible to realize it in dilute gases, where the conditions are sufficiently close to the ideal model of Einstein. And that was only in 1995. That's what I meant when I said Bose-Einstein condensation was first achieved in 1995. You could say it was already achieved in 1938, but it was not really in clean form as Einstein predicted it. And well, there is more to it, namely that liquid helium is just liquid helium, and you are simply stuck with it. But with these dilute alkali gases, you have the possibility to tune the parameters and really make lots of experiments which are not possible with liquid helium. So this is a very important additional aspect. Now comes here a group of heroes on the experimental side, namely the people that first achieved this creation of Bose-Einstein condensation. And this is here the leaders of the group in Boulder, Colorado, Wieman and Cornell, and at about the same time at the MIT in Cambridge, USA, Wolfgang Kettel did the same thing. The meaning of these pictures I will discuss also very soon. Now this creation of Bose-Einstein condensation is now done in many laboratories around the world, among them here in Singapore. This is an announcement from the September 5th, 2009 about the first creation of a Bose-Einstein condensate in Singapore. So this was really a news item, and I think that's totally justified. Now I'm going to talk a little bit about the theoretical basis of Bose-Einstein condensation, and I'm going to start here at a very low level. I'm not really assuming any knowledge of quantum mechanics, although I know that, well, maybe all of you are familiar with quantum mechanics, or most of you. So let's discuss first briefly that the two basic ideas of quantum mechanics that are necessary to know about in order to appreciate the difficulties and the way of producing Bose-Einstein condensate. The first is that material particles, which you might first think of simply as little grains of sand or little mass points, that they have wave properties. And the wavelength is related to velocity and the mass by an equation where you have a Planck's constant, which is an extremely small quantity and measured in standard macroscopic units. And it relates to the wavelength by this formulation, so that the momentum, the mass times velocity is Planck's constant divided by the wavelength. And this was predicted theoretically by Louis de Broglie in 1924. This is the first of his two ideas. The second idea is that when you have particles whose motion is in some way constrained by external force fields or by putting them in a box, they cannot have arbitrary energy. And the possible values of the energy, they correspond to standing waves. And well, just to have an order of magnitude of the distance between these levels, so to say the quantum of the energy, this is the order of magnitude. And you see also here the wavelength goes here in the denominator, and this very small Planck's constant here in the denominator is in the numerator. And this idea was made precise by Erwin Schrödinger in 1927 by his Schrödinger equation, which I am not writing here. This is, so to say, my substitute for the Schrödinger equation. Okay. I hope that will be forgiven. And now, waves. Well, first I will say a few words about classical waves. The hallmark of waves is the possibility to interfere, namely to either strengthen themselves, or rather that the two waves or coming from different sources, they can partly strengthen each other, or they can partly annihilate each other. Namely, where the wave crests and the wave troughs, where they meet, then you have annihilation. Where two wave crests meet, then you have reinforcement, and this leads to the interference patterns, which are shown here with the surface wave of water. They come out here of two holes. Here is a plane wave, and here are the waves that go out, and you see here this typical interference pattern. Here is also the interference pattern. This should be rotated 90 degrees because this is supposed to be the strength of the wave in a different direction. I have drawn it like this to compare with a picture which comes a little bit later. Standing waves, classical standing waves, you take a string, you see that it can only have certain wavelength and be a standing wave. Namely, here is the largest wave, and then you can have 1/2, here you can have 1/4, 1/3. Of course, in a quantum system, everything is a little more complicated, but the general idea is already expressed in this simple picture. Now, despite this analogy, there are, of course, very important differences. And now I'm going to talk about them briefly. First of all, the amplitude of a classical wave is always a real number. This is something which you can measure with a measuring instrument or with a stick. However, the amplitude of a quantum wave is a complex number, which involves square root of -1. So this is definitely a more complex, also in the technical sense, complex phenomenon. Now, here comes a very important and in fact a strange property, namely that classical waves, they describe factualities. They describe, so to say, real situations or states of affairs, but quantum waves, they describe probabilities. These are probability amplitudes in the terminology of quantum theory. Now here is another, the last point I want to mention here is that the wavelengths of quantum waves are usually extremely small. And it's only for very small masses and low velocities, which you, in order to achieve it, you have to have very low temperatures. that these wavelengths become macroscopic. Here are some numerical examples. Well, here are the formulae for the wavelength. Set the wavelength is Planck's constant divided by mass velocity, and if you have atoms in a gas, the velocity is related to the temperature by the formula which tells you that the kinetic energy is about Boltzmann's constant times the temperature. So you can insert this formula for V here, and then you get Planck's constant divided by square root of Boltzmann constant times T times mass, and here are the numerical values. You see these are very little numbers here. So if you take a soccer ball or a football at, let's say, 50 kilometers per hour, which is not very fast, well, the wavelength is about 10 to the minus 35 meters. Another ball, however, much smaller, which I will show you in a minute, is the so-called fullerene. This is really a molecule. It's a molecule of carbon atoms, of 60 carbon atoms, and it looks a little bit like a football. And here I have taken the temperature from 900 Kelvin for a specific reason. And here it has also a very small wavelength. This is a picometer. That is the order of the wavelength. Now here we come to rubidium, and that is namely I'm choosing rubidium because that was the first atomic gas that was brought to Bose-Einstein condensation. If you take it at 3 Kelvin, which is of course a very low temperature, but still not low enough for Bose-Einstein condensation, then the wavelength is about 10 to the minus 9 meters. But when you are really down to here, the nano-Kelvin range, then you really are getting macroscopic wavelengths. So this is a millimeter here. So there you see that you are really getting something macroscopic. Now come here a few graphs where I'm going to discuss briefly wave-particle duality. This is not very important for Bose-Einstein condensation, but you can hardly escape it when you are talking about quantum mechanics, so I will show you a few slides about that. First is that quite contrary to classical waves, the interference patterns of quantum waves emerge from many random events. They build up, so to say, gradually if you make repeated experiments. So quantum mechanics leaves rooms for uncertainty. For those who don't understand German, you see this says here, Institute of Quantum Physics, that's self-explanatory, and you are either here or there. And this is all you can say. Now here are some 3 slides which my colleague in Vienna, Markus Arndt, borrowed to me, and this is what he shows usually, because his speciality is to do quantum football, not with FIFA balls, but with fullerenes and more complex molecules. So here is a quantum, here is a football game where this player here, he kicks balls through a gate, and here is here is the heap of balls that will pile up. He is trying to hit in the middle, of course, so they will have a certain concentration here in the middle, but he will not be successful every time, and he will, of course, then kick off here of the boundaries. So this is how it will look. If the other gate is open, then it will look a little similar, but with a bias to the other side. And now you open both gates, and you would expect that what you see is simply a superposition of these 2 piles. But that is not the case, because, if this was a quantum football, you would see that there are certain places where the ball is not going, and although you would expect more balls there, but in fact it is because of that. And because of the interference between the quantum waves. Now, you cannot demonstrate this with classical football, but you can do it with full range, which are called buckyballs. So here is a classical football, and here is a buckyball, which you have to go down then by a factor of 1/200 million. And then you have here a carbon molecule of 60 carbon atoms with a diameter of about 1 nanometer. And here is the outcome of a real experiment, namely from the group of Magnus Arndt. And here you see this beautiful interference pattern. This is quite remarkable, because the wavelength in this case, as I said before, is about 1 picometer. It's extremely small. Okay. Now, to sum up, one can say that nature, according to quantum mechanics, is indeed strange. And I don't know if Charles Adams intended to say something about quantum mechanics with this famous cartoon here, but it certainly gives you, so to say, the flavor of it. And what to do about it? Well, we have to live with it, and we can also try to make good use of it. And that is precisely what is done in quantum technology. Okay, now I'm going to talk about Bose-Einstein quantization again, and I find it always very convenient to use this picture here, which is borrowed from the website of the Ketele group. Well, it is nice, although it does not quite capture a fine point. I will tell you about it at the end. Anyway, so according to this description, you should start here at a high temperature. There you don't have to think about the Broglie wavelengths. You can think of the atoms as little billiard balls, and they are moving around, and they have some average distance between them, and this is called d. So the thermal velocity is v, that's the square root of k times the temperature, or proportional to that, and the density is 1/d². Now, as you lower the temperature, the de Broglie wavelength starts to become noticeable, because it goes like 1/the velocity, and the velocity goes like square root of the temperature, so the de Broglie wavelength goes like 1/square root of the temperature, and it starts to become noticeable. So you should now not think of the atoms as little billiard balls, but rather as little wave packets of a size comparable to the de Broglie wave. Now, if you go even farther, and namely to a certain critical temperature, then the wave packets really start to overlap, namely the wavelength becomes comparable to the mean particle distance. And this is where Bose-Einstein quantization starts. And if you go really all the way down to 0, you have a pure Bose-Einstein quantization, one giant matter wave, everybody sits in the same state. Okay, so this looks very convincing. So why isn't this a complete explanation of Bose-Einstein quantization? Well, the certain point is that this picture here does not seem to make any use of the dimension of the system. This argumentation would be equally valid, as does appear, for a three-dimensional system or a two-dimensional or even a one-dimensional. And this is not true, because a more detailed analysis shows you that Bose-Einstein quantization does not take place, at least not in the standard sense, in lower dimensions than 3. And the point that is missing here is namely the so-called density of states, namely how many states you have per, so to say, interval in the energy space. But this is a fine point that I'm not going to discuss here. I just mentioned this for the benefit of the students that might be here, that even if this picture looks beautiful, you should remember that there is one more point. Now, but this is quite interesting, however, that you see that to generate Bose-Einstein condensation, the only thing that you have to do is to make the mean particle distance smaller than 1 over square root of t times some constant. So you can apparently do this for any t if t is small enough, or for any t if t is small enough. So by this formula alone, you could have Bose-Einstein condensation at the room temperature. So why don't you have that? Well, the reason is that in order to that this formula makes sense, you need to have an approximately ideal gas. And this means that the mean particle distance must be much larger than the range of the interaction. And this requires sufficiently large t and hence very small t. So now you want to achieve small t. So what are the techniques for doing that? And this is usually done by combining two techniques. One is laser cooling, which is sort of you simply break you stop the atoms, or rather you reduce their velocity by shining on them with the laser at an appropriate frequency. It is like breaking them with the laser, but that is not enough. You also need another mechanism, which is evaporate cooling, which is exactly the same method as you use for cooling your coffee. If your coffee cup is too hot, you blow it up, and you blow, so to say, away the hot molecules. And however, this will increase d because it will lower the density. So this will increase when the temperature decreases. So there is a certain compromise you have to do here, namely, you have to achieve the low temperature before the gas is too dilute, that is to say, before D has become too big, because otherwise this condition cannot be satisfied. So this is something which you do in special devices, which are called magneto-optical traps. This is a schematic picture of it. Here are laser beams, and here are magnets. This is a schematic picture of the Boulder original apparatus. Well, here is the real Singapore trap. So this is how this hardware looks like. It's not very big. I mean, it be something of this size here. And here is a picture which shows you this race. So I ask you to look here at this right side here. Well, here is the critical temperature, which depends on the density. And here is the real temperature which you achieve by this evaporate cooling, namely by blowing away the hot atoms. And what you are seeing here is the distribution in velocity space. And when you have this peak, this means that everybody, so to say, is as slow as it can be. You have everything sitting in one state. And that happens exactly when this temperature here wins over the critical one. You see, it is trying to escape from the T, but this is faster, so you really get condensation. And this is now a more beautiful outcome of this. This is again the picture of the original experiments of Ketterle. And you see here the velocity distribution at a high temperature or relatively high. Here you have already some condensation, and here you have as much condensation as you can get at very low temperatures. And please note that this is really a picture in velocity space, or technically in momentum space. Nowadays you can even do Bose-Einstein condensation on microchips, which is important also for certain applications. However, now I come to the theoretical side, and I would like to emphasize that Bose-Einstein condensation, in spite of these really spectacular experimental successes, still poses very difficult theoretical problems. Now, for an ideal Bose-Einstein, there is no problem. In fact, the argument of Einstein, although it is was put forward in 1924. It is as valid today as it was then, even if it didn't have the full formalism of quantum mechanics with Hilbert space and density matrices. You simply translate it word by word, and it's perfectly valid and good. However, what makes it difficult are the interactions between the atoms. They are unavoidable and they are important. I said, of course, helium is very far from being an ideal gas, so you cannot expect to have this pure situation there. But even if you have dilute gases, these interactions are important. And in fact, this is simply a fact. You can say it's a scandal, maybe, even. When interactions are taken into account, the situation changes dramatically. There is still no general proof, really starting from first principles, of Bose-Einstein condensation for those who know in the technical sense of in the thermodynamic limit, not even in the ground state, not even for t equal to 0. And this picture is intended to show you that interactions are in fact important. This is the density distribution of a trapped Bose gas in a magneto-optical trap. And this here curve is the curve as it would be if there were no interaction. And this is the curve, these measured points here if there is interaction. And this curve here is based on the so-called Gross-Pitayevsky theory. This is a theoretical description which will predict you how the interaction really affects this density profile. It fits very well, but the main point for this picture was to show you that the interaction is important. Now there are, however, cases where Bose-Einstein condensation has been proved rigorously. For, so to say, realistic interactions, there are also simplified models where you can prove it, but now I'm really thinking about starting with the full quantum mechanical many-body problem. One is the case of a specific limit, so-called Gross-Pitayevsky limit, where the interaction energy of the particle is of the same order of magnitude as the energy gap in the trap. Another one is a model. It's a very special model. It is not the most popular model among theoretical physicists, but this is a special model of the atoms which are trapped in an optical lattice, and where the number of particles, however, per lattice side is exactly equal to 1/2. This is the method simply does not work otherwise. I am here not voting in all I'm saying here. I'm not quoting the authors or the contributors just to say time. These names would maybe not tell you but too much, but of course these things that I am telling you about here have been achieved by many, many people, and which I will not mention in all cases. I just wanted to say that as a general statement. Now, what are optical lattices? Yeah, this is one of the new things which came up, so to say, new experimental technology through these studies of Bose-Einstein condensates, and this is a very important development. This is one of the steps towards this tuning, which I mentioned, of the parameters of the system. Well, optical lattices you obtain by having lots and lots of such crossing laser beams. Here is a lattice where you produce, so to say, two-dimensional, you produce, so to say, one-dimensional systems, if you like, here. There is, in addition to what is shown here, there is a trapping device which will, so this does not really reach to infinity in all directions, but there is a finite size. But these many points here, these lattice points, are obtained by laser beams which point in different directions, and they generate, so to say, a lattice of points where you have a a potential with special properties. And now this is a very, very interesting fact, which has quite some history, which I'm not going to tell here, is that even if you do not vary the temperature, you can produce and you can sort of say, you can turn on Bose-Einstein condensation and you can turn it off again by varying the parameters of the optical lattice. Namely, by varying the strength of the laser beams, you can vary the depth of the potential waves, wells in the optical lattice where the atoms sit. And when you have a shallow well, then you have Bose-Einstein condensation and ensuing interference pattern when the trap is opened. If you have deep wells, then you have localized atoms and you have independent waves and no interference patterns. And this is the results of an experiment in Munich by Greiner, Hensch, and co-authors, where you really see this. This is a very shallow well. In fact, here is no optical lattice. There is only this big external trapping potential. You have here a sharp interference. And then you have here deeper wells. Well, first of all, here you have still, you have interference patterns, but they will disappear if the well is too deep, because then the atoms become localized. But this is in fact fairly sharp. I mean, it really takes place about here. Okay. Now here is I just couldn't resist by showing you at least one picture of from research of in fact, yeah, Philip Soloway was here, and myself and our colleagues in Princeton, which is really about this model I mentioned, where one can really prove that there is Bose-Einstein condensation in one corner of the parameter domain, and there is no Bose-Einstein condensation in another one. So this is really a result of a rigorous mathematical analysis. This is not based on the Hubbard model, which many of you will know. This is based on the Alcorn-Landis gas. Okay, now, why is Bose-Einstein condensation so difficult to prove mathematically? Well, I had already mentioned it has to do something with the spontaneous breaking of a continuous symmetry, which is formally similar to the breaking of rotational symmetry in a ferromagnet. And when you have continuous symmetries, then it's very difficult to break them, because you have fluctuations of long wavelength, and they cost very little energy and tend to restore the symmetry. The symmetry which is here at stake is not really a concrete symmetry like rotational symmetry in the ferromagnetic. It's on a more abstract level. It has to do with particle number. But this is mathematically, it is exactly of a similar kind. Now I come to the last 15 minutes, now so to say the second half of my title, gradually, namely the vortices. And then I first have to say a little bit about the general connections between Bose-Einstein condensation and superfluidity. What is superfluidity? Well, it can mean flow without friction. This is what it originally meant in the connection with superfluid helium, which you could really make flow through very narrow channels, apparently without any viscosity. But there is a weaker definition which is not equivalent to this, namely that the system will not notice if you move the boundaries a little bit. And now I would also like to stress that superfluidity is conceptually distinct from Bose-Einstein condensation, but it is usually implied by the latter. Exactly why that is so is a complicated matter and not really fully understood, because there are also instances where it is the other way around. So this is, you should not think that superfluidity and Bose-Einstein condensation are synonymous. In fact, in helium, at extremely low temperature, it's almost 100% superfluid, but it may be only a few percent Bose-Einstein on that. Anyway, but what is remarkable is that when you are in a superfluid, the velocity is related to phase, namely the complex phase of the wave function of the Bose-Einstein potential. And the formula, this is the most complicated formula I'm showing today. It even involves the gradient, which I will not explain what it is. If you don't know what it is, I cannot do that in 10 seconds. And here is Planck's constant, and here is mass. And the velocity is related to the phase in this way. And now this has something to do then with, or has influence on the concept of circulation in the superfluid. Now circulation, what is circulation? Quite general. Now this is not limited to quantum systems, but is, so to say, hydrodynamics. In a fluid or a gas, if it is flowing with a velocity, the circulation around a closed loop, if we have a closed loop, is defined simply as the integral of the velocity along the loop. The vorticity at some point is defined as the circulation around a very small loop and closing the point and divided by the area. And you let them, to make it precise, you have to take a limit, of course. But I say a small loop, I mean, infinitesimal. And the vortex, I'm now using a rather generous definition of this, is a region with non-zero vorticity. Now, of course, vortices are quite abundant in nature, and this is maybe the most familiar, maybe simply a bathtub vortex. But vortices, in fact, they come in many sizes. Here is a vortex which is about 100,000 light years in diameter. Now here are vortices which do not really exist, but were conceived in the 17th century by Descartes in competition to Newton, so to say. This was supposed to be an explanation of the movements of the celestial bodies. As we know, it was Newton who was victorious in that battle. Now here is a vortex on Jupiter. Here, to compare with the size, this is the Earth on the same scale. So this is quite a big vortex. Here is also a big vortex on the Earth. And here is quite a big vortex. In fact, this picture, I think, is taken here in the waters of Singapore. And here is a smaller vortex connected to the propeller of an aeroplane. But what is of concern here are quantum vortices. And this is a picture of quantum vortices. And the size was, well, this is of course a blown up picture here. So this is about the size of a typical Bose-Einstein vortices. So this is a fraction of a millimeter. But it's nevertheless, in a way, macroscopic. Okay, now well, I want to bring here an important message about quantum vortices, namely the quantization of the vortices. And in order to understand that, you have to first understand that there is a difference between what is sometimes called rotational vortices and irrotational vortices. Now here is a picture which is supposed to show you, to show this. This here, well, this is so to say the starting position here. And then you have here two possible scenarios. One is so to say a rigid rotation. If this was simply a glass of water, this was swimming along the water and you were rotating it, then you see that the leaves will simply follow the rotation. They would also rotate, so to say, internally. And they would, the whole surface here is rotating and they will also rotate again. So there is vorticity here in the sense I have made precise before, everywhere, so to say, because this little leaf is rotating here by itself, not only around this point, but also by the center of it. Here is, however, quite a different situation when you see the orientation is not changing. It's, so to say, as a situation where it's rotating like that. And this is what is called the irrotational vortex. This is a situation where the vorticity is simply sitting here, and there is no vorticity here. And this is the basic fact about quantum vortices, namely that quantum vortices are irrotational. The vortice is concentrated in vortex lines, or in two dimensions in vortex points. And vorticity, it's not only concentrated there, but it's quantized in units of Planck's constant divided by m. Now this was probably first realized by Lars Onsager, who was a great physicist, chemist, and mathematician. I could really tell you stories about Onsager, but unfortunately there is not time for that here. And this was just a little remark in a footnote of a paper in 1949, without any explanation. But in fact, it's not so difficult to understand in a naive way if you just say that, well, you have to have you look at a closed loop, and a matter wave which is going around, and it has to close. So that the circumference of the closed loop has to be an integer multiple of the wavelength, and now you insert here the Broglie relation, and then you see that the multiple of velocity and the circumference is n times h over m, and for those who know what is an integral, then here is an integral, but you don't have to know that. Anyway. Okay, and here is also another picture which shows the same, namely that it simply goes in jumps. Now, the creation of a contact vortex in a rotating container. Now, this is experimental pictures from the group of Jean Dalibard at the École Normale Supérieure in Paris. Namely, you have you put Bose-Einstein condensate in a container, and then you start to rotate it. And then, to begin with, nothing happens. You increase the rotation velocity, and then all of a sudden you see a vortex. You increase it further, and the number of vortices increases, and you see that the vortices also, they arrange themselves in a regular pattern. And you see it more beautifully here, where you have many vortices. And you see they arrange themselves in a triangular lattice, where the unit cells are hexagonal. Now, why are vortices favorable? Well, a simple way of understanding is to say that what is favorable is to minimize the energy in the rotating frame. And the energy is here is the kinetic energy. And since this is a super fluid, you move the boundary, but the fluid will to begin with not move. So in the rotating frame, it's moving in the opposite direction. So after a while, this motion in the rotating frame is creating quite a big velocity, and it pays off to try to compensate. And that is done by creating vortices, and you can only do it in these integer steps. And so you should think now of a situation. This is pretty high velocity. This blue, so to say, indicates the rigid rotation as it looks in the rotating frame. And this is now a velocity field, this blue one, which is simply proportional to the distance from the center. And it's being compensated by all these vortices. And that namely reduces the energy. Now, under rapid rotation, the vortex lattice can even melt. Well, these pictures here are, it's a little complicated to describe what is really being done here, because you are really stirring with a laser. But my main point here is simply to show you that these pictures of this kind are not the only ones that you can get, and under certain circumstances you can get something like this, in particular a hole here in the lattice, and the vortices are disappearing. This is something which is called a giant vortex, and this is a very interesting subject to understand mathematically how exactly this comes about. It seems to contradict what I said before, but the reason is that you have to take centrifugal forces also into account, and then you will see that this is really what happens. Now the last thing, I have only a few minutes, so I'm just going to mention here, I have two view graphs just to mention a topic which is, so to say, quite modern, or well, I mean, things are moving very fast in these topics. Mathematical physics, of course, moves in a little bit more leisurely pace, because you want really to understand things from a mathematical point of view. But this, the so-called lowest Landau level physics in the context of rotating gases is a hot topic both in theoretical and also in mathematical physics. The basis of this is that mathematically rotation has the same effect as a magnetic field. It's not so simple maybe to explain it, except that this picture here, for those who know some physics, this will remind you of these voltages, will remind you of currents, and these little lines here of the magnetic fields around currents. So this is a good, in fact, good analogy. But there are very interesting connections which can be made with the quantum theory of electrons in strong magnetic fields. In such situations, you group the quantum states into so-called Landau levels, and then when the rotation velocity in a quadratic trap is almost the same as a trap, frequency are confinement into the lowest Landau level occurs. And here the properties of the rotating gas are determined by a subtle interplay between rotation and the interaction strength. Namely, Bose-Einstein quantization can break down and the vortices can disappear. And instead you have a host of phenomena which have to do with strong correlation in this complicated many-body system. And you expect to have analogies in the Bose domain of what is known as a fractional quantum Hall effect in the electronic domain. And just as is the last slide, in fact, in this regime there are many open problems. And here is just one example, namely establish rigorously the so-called ERAS curve. I'm just putting this curve here for the benefit of people who are already familiar with this stuff. Those who are not, I mean, it really doesn't matter. I just want to tell you this is a curve which illustrates in the many-body context the interplay between the interaction between the particles and the rotation velocity, which is here measured in terms of the angular momentum. And this is in technical terms the joint spectrum of these two operators. Vortices, you can, here you have, so to say, parameters are the value, are the common eigenvalues of these two convoluting operators. And the regime where you can have vortices and where you can have a description by a single wave function, that's just a tiny little region here, along the axis here. Whereas this rich fractional quantum Hall stuff should be here. This is the conjectured and numerically computed curve, but to analyze this mathematically is a really very interesting subject. And with this, I think I have exactly now finished my time, so the only thing that remains is to say thank you very much for your attention, and many thanks for the great time that I and my wife are having here in Leipzig.